want you to do something right now. On your computer, go on and open your terminal. Go to Python and type in 0.1 plus 0.1. This is 0.2 obviously, right? Next, type in 0.1 plus 0.2. Now you've got an unexpected result there, right? Aren't you curious why in the world this is happening? If so, stick until the end. Because trust me, when you finally understand this, you'll suddenly jump out of your chair and start dancing the Macarena. What I'm about to talk about is that interesting. Today we will explore the reason why 0.1 plus 0.2 equals an unexpected result in Python. Here are the three concepts we're going to discuss today. For starters, we will talk about the binary system. Computers only know ones and zeros, yet it can display 2s, 3s, 4s, or even 3,583s. This system that the computers use to represent many symbols with just 2 is called the binary system. Now, how can they do this? What's happening when it's converting the ones and zeros to other symbols? In order to understand this, we must talk about the system we use every day to represent numbers, the base 10 system. The base 10 system has 9 symbols, 1, 2, 3, 4, 5, 6, 7, 8, and 9. We use these 9 symbols to represent many other symbols by reusing the same symbol over and over again. This happens by something called positional notation. What happens is that the number gets greater and greater as the digit increases. In the case of the base 10 system, it gets greater by 10. Take a look at this number. In the ones place, the 5 is multiplied by 10 to the power of 0. But in the tens place, however, the 3 is multiplied by 10 to the power of 1. In the hundreds place, it's 10 squared. In the thousands place, it's 10 cubed, and so on. As you can see, the number there getting multiplied is increasing by 10 each time the digit increases, and hence it's a base 10 system. So getting back to the binary system. In the case of the binary system, as you may have realized, the number they get multiplied increases by 2 each time the digit increases. So say 11000. In the ones place, the 0 is getting multiplied by 2 to the power of 0, which is just 0. And in the seconds place and the fourth place, the zeros are getting multiplied by 2 to the power of 1 and 2 squared, which also result in zeros. Now in the 8th place, the 1 is multiplied by 2 cubed. In other words, it's 1 times 8, which equals 8. In the 16th place, the 1 is getting multiplied by 2 to the power of 4, which will equal to 16. And when you add these values together, it becomes 24. So 1100, 0 when converted from binary system to the base 10 system becomes 24. Here's another quick example. Let's consider 1001111. All the values will be multiplied like this, will equal to this, and when you add them, become 155. Easy, right? So now that we learned how the computers represent integers, let's take a look at how they represent decimals, or floating point numbers. It'll get a lot more complicated from here, but no worries. Just understand the basic concept, and that's okay. Since, remember, our goal is to understand why 0.1 plus 0.2 equals what we saw, not to understand how computers represent decimals. In Python, computers use a system called IEEE 754 to represent floating point numbers. Because IEEE 754 is a long name, let me just call it bananas. In this banana system, they use 64 bits to represent floating point numbers. Out of these 64 bits, 1 bit represents the sign of that decimal, 11 bits represent the exponent, and the last 52 bits represent the mantissa. The mantissa is kind of like the part that carries the most essential information. For example, in the case of this number right here, the sign is positive, the exponent is 3, and the mantissa is 123.45. Now, let's actually take a look at a number that uses the banana system. In this number, this part represents the sign, this part the exponent, and this part the mantissa. Let's take a look at them each. Now, the sign is positive if it's a 0, and negative if it's a 1. In this case, it's positive. Then for the exponent, when converted to the 10 base system, it's a 1026. But the thing is that we have to subtract this by 1023. Why? Well, in the bananas system, the exponent of a number is biased by 1023. This bias lets us represent both positive and negative exponents using only non-negative values, making things more simple. Thus, we must debias that number by subtracting it by 1023 in order to get the actual value. And 1026 minus 1023 is 3. So for this number, the exponent is 3. Let's talk about the mantissa now. Since the leading bit is always 1, we add a 1 next to the mantissa, which is 0, 1, when you cut off all of the unnecessary zeros. So it becomes 1.01. Therefore, what we do now is multiply this 1.01 by 2. Since it's a binary system, raised to the power of what we got earlier, which is 3. So 1.01 times 2 to the power of 3. And when you do this in the binary system, you basically shift the decimal point of 1.01 by the exponent, which is 3. So you'll get 1010. And when you convert 1010 to a base 10 number, it becomes this. And when you add these, you get 10. Thus, this number converted to the base 10 system is 10. So in a nutshell, here's how to convert integers in the bananas form to the base 10 form. First, you figure out the sign, then you figure out the exponent and debias it by subtracting it by 1023. And next, you put a 1 in front of the mantissa with the decimal point in between. And then multiply that by 2 raised to the power of the exponent you got earlier. And lastly, convert that into a base 10 number, and you've got that answer. To make it crystal clear, we'll do one more example. Let's take a look at this number. The sign is positive, and the exponent is 1027. When you debias this by subtracting 1023, you get 4, which is the exponent. Then you do 2 to the power of 4 times the mantissa, which is 1.101 rounded. And 2 to the power of 4 times 1.1 is 11000, since you shift the decimal point 4 times. Because this is equivalent to 24 when converted, the answer is 24. Okay, so we've been looking at integers that are written in bananas form. But what the banana is really good at is representing floating point numbers. So now we'll look at floating point numbers represented in bananas form. Let's consider this number. The sign is once again positive and the exponent is 1023. And as you may have realized, when debiased, this becomes 0. So basically, we don't shift at all. Hence, 1 point the mantissa stays as 1.1. Now, here's what's different when converting floating points instead of integers. We must interpret this answer, which is 1.1 in this case, as a binary number. Therefore, we must convert this to a base 10 number in order to get the actual number. The right side of the decimal would be multiplied by 2 to the power of -1, and 1 times 2 to the power of -1 is 0.5. And the left side of the decimal, or simply the ones place, is 2 to the power of 0, as you know. And 2 to the power of 0 times 1 is just 1. So the equation is 0.5 plus 1, which equals 1.5. Thus, this number is 1.5. Okay, this is how you represent floating point numbers in the banana system. Once again, just understand the basic concept and you're okay. Just remember not to say bananas when explaining this to someone else. And last but not least, we will take a look at why 0.1 plus 0.2 does not equal 0.3. All we have to do to figure this out is see the bananas version of 0.1 and 0.2. And when you actually do this, you'll see that these two numbers mantissas are the same. This is because there's a repeating sequence right here, where 1100 keeps on repeating itself over and over again. But the problem with this is that we only have 64 bits. Because of this, sooner or later, it must be cut off. As you can see, these two mantissas are cut off at the end. Hence, we cannot have the exact numbers stored. This is why the result is not accurate. So, this is why 0.1 plus 0.2 does not equal 0.3 in Python, because the correct value for each of the numbers is not stored in the first place. Thanks for watching until the end, and congratulations! Now you've mastered the binary system, how Python represents decimals, and why 0.1 plus 0.2 does not equal 0.3. Go on and show off the people out there.
Now, let us return to our everyday lives.